Hello. So in this video, we're going to be talking about sort of a classic application word problem, related rates. So it's worth a mention, whenever we have rates involved, chances are pretty much guaranteed calculus is lurking somewhere in the situation, like, serial killer lurking in the basement kind of deal. So often we don't have all of the primary information that we need. Rather, one rate of change is sort of somehow loosely based on some other rate of change. So when we have that kind of a setup, then, this idea of a rate dependent on another rate, this is usually what we mean when we refer to related rates problems. So related rate problems are very general. They can encompass all kinds of different scenarios, contexts, setups, equations, all kinds of things. And for that reason, there's no single formula or even a type of formula or equation that you use to solve a related rates problem. So what we're going to do is cover this sort of general framework of an approach that should help you determine sort of how to approach and hopefully solve one of these related rates problems. So let's start sort of with an example here. So let's say we have a tank and that tank is leaking, and the ensuing puddle that it makes is this bizarrely perfectly circular puddle for our ease. And we'll say that this is increasing at the rate of about 25 square inches per minute. Okay, so the question is, how fast is the radius increasing when the radius itself is about 10 inches? So we want to know how fast the radius of the overall puddle, how fast it's increasing, right? That's the key. That's the rate part. When, and sort of, we need a moment in time, right? And we want to know when the radius is at 10 inches. Okay. So step one, as is pretty much always the case in math problems, step one, we want to sketch a picture. So this can be a literal sketch like our circular puddle here, or it can even be, a sequence of words or something with arrows sort of determining what goes to what and how things are sort of, related together. But the idea here is this will help you crystallize exactly what's involved in the problem. And in particular, this is a great way to get sort of a bird's eye view of the structure of what's happening with this. So this is helpful for the next step, which is applying the language of math. So here, for example, our sort of goal is to assign all of these variables, assign letters to everything that's sort of involved. And in fact, it's even better to sort of overdo it at this step and be able to cut back later than to try to backtrack and figure out what might be missing. So the idea here for our circular puddle, we're going to need some sort of radius bit, right? So we're going to need R. We're also going to need the area, right? The area bit came up. We talked about sort of per minute, so time is a factor. So we're going to have a t lurking somewhere in here. And in fact, one of the sort of phrases, right, that I pointed out was this idea that the area is increasing at a rate, right, of 25 square inches per minute. So this rate is a change in area over change in time. So we would represent that as this dA dt, right? So that's the change in area over change in time. Step three, we want to write down an equation. So in particular, we want to have an equation that sort of ties this stuff together and relates what we're actually after. So this is going to be tricky because there might be a bunch of options, or there might be no obvious options at all. And unfortunately, there's no sort of systematic way to determine what the right equation is, the right formula. So this is usually the difficult part of the related rates part. So here I have information about the area. I have what I want, right, is that change in radius over time. So I want to relate my area and my radius. And the hope is that the change in time bit will come in with the calculus. So I'm going to start with the area of a circle, right, which relates my area, my A, and my radius R. It doesn't have t in it, obviously, but the hope is that I can generate that. So that is step four, which is figuring out how to generate the rate that I'm after. So typically you generate that rate by taking a derivative, almost always, because we're usually talking about rates over time, right? Change in area over time and radius over time, almost always that's going to be a derivative with respect to time, t. Doesn't always have to be, but it usually is. So what I'm after is the change in radius over time. So what I'm going to do is take my original formula, my area equals 2 pi r squared, pi r squared, and take the derivative to get my change in area is 2 pi r change in radius. So notice here that this is sort of inherently going to be an implicit derivative, right? Because the thing I'm taking it with respect to, t, is not the variable that I am taking the derivative of, right? So when I take the derivative of a with respect to t, it becomes dA dt. When I take the derivative with respect to r of t, I get a dr dt coming out as well, right? So it's worth a mention here that it's sort of useful to keep track of that. So here I'm using this dA dt rather than a prime because it's telling me that that's where that's coming from, right? It's telling me that I have that dt bit, this over time bit, instead of just having a prime, which doesn't tell me what it's with respect to. And sort of that's a key element of this problem. All right, step 5, now we want to start substituting stuff in. So one of the things that's sort of easy to miss about our previous steps is that I've left everything in terms of the letters, right? When I did area, I had area equals pi r squared, and there was a point, right, where it's like, oh, when the radius is 10, but I didn't put in 10 yet. I just left it as pi r squared. And we're going to see sort of exactly why that's important. At this stage, we want to try to substitute in as everything that we can. If there's pieces missing, which happens, first we want to try and see if we can sort of figure out what those pieces are in some other way rather than trying to scrap everything and come up with a different formula to start with. Because a lot of the times there are ways to sort of recover information that's missing from the original statement. Here, I have this dA dt as 2 pi r dr dt. dr dt is what I'm after, so I'm going to see what of the other pieces of information I know. I know dA dt is 25, right? Because that was the change in area over time. The amount of water that's getting put in is that 25 square inches per minute. I know my radius at the time I care about is 10, so I can plug in my r equals 10. And if I plug that stuff in, and then I can solve for my dr dt by moving the other bits over, I'm going to get my dr dt is 5 over 4 pi inches per minute, right? Because my area was in square inches, my unit is inches, and my time was in minutes. Okay, so this would be how I'd solve for the dr dt. Now, as a comment, I mentioned before, right, that it was important somehow that I didn't put in my radius of 10 in my original formula. And the key here is that you don't want to sort of substitute anything in until after the derivative step, if you can. So if I had done that beforehand, right, if I was like, oh, my a equals pi r squared and I know r is 10, well, then I'd have area is 100 pi, which is like, okay, sure. But then if I took a derivative, 100 pi is a constant. So taking a derivative, I get that dA dt is 0. But that can't be right? Because the original problem told me that dA dt was 25. And so by substituting in that r equals 10 sort of too early, this is a big red flag that now I'm getting contradictory information. Something has gone wrong as a result because I'm getting sort of information that can't possibly be true. And in this case, that the part that sort of went wrong is that I don't want to substitute in anything until I take the derivative. Usually that's after that is when I want to try to substitute in the actual numeric values. Okay. All right. So what do we do? So we've introduced this idea of related rates, and we went through this example, right, of our leaking tank into our nice, conveniently circular puddle. But this algorithmic approach, it's more of a sort of series of general guidelines to help you sort of figure out a way to approach these problems. But each problem is different. So sometimes these steps are sort of more crucial than others. Sometimes there's a little bit extras you need to do, or sometimes certain steps don't really apply. This is definitely one of those things where you want to watch as many of the example videos as you can and do as much practice as you can in order to sort of acclimate and figure out how to approach each problem, because each problem is slightly different. All right. So that's that.